an overlog meeting about containers, and we'll be doing a introduction to containers. So if you haven't used them before, hopefully after this, you're going to be able to at least make yourself dangerous. We will be covering more than just the bare basics, but not too deep in what containers do and how they work. If we did, we would not have enough time, but feel free to ask questions and follow up. That said, please make sure you're muted. You should be muted on entry now, but if you're not, we may hear an echo and stuff like that, and we will try to avoid doing that. When you want to talk, feel free to unmute yourself and talk, and you do not have to wait until we're all done. Feel free to interrupt and do all that stuff that we have. So, Linux containers. And I'm going to use the word Linux containers very specifically. Windows is finally catching up, and Windows is beginning to actually not only have native containers, but with full features. And the idea of how containers work are very different between the two. So when we do this talk here, I will be focusing on the Linux world of containerization, how that works, and specifically maybe how it does not work as we go through this. But Linux containers is basically what I've been doing for, wow, depending on how you define it, almost for the last 10 years. It's been part of my job, is to deal with containers one way or another. And as I will get into it just in a moment, containers are nothing new for Linux. So here's a little bit about what I'm going to cover today. And you will see, and you should be able to see that on my screen too. There's a URL on the top of it. You can go there anytime you want, and particularly after this talk, this is a site that is up 24/7 all the time. And you can go to most of the stuff that I'm going to show. There are different examples in there, and they go actually deeper in some of the things that I'm going to show. But it's a complete featured test system where you get a command line that you can do whatever you want to. And there's a guide on the side that tells you about how it works and gives you example commands to show how things work. So you can do all this yourself, and you can actually grab. So part of the slides that I'm going to show comes from the presentation from that site. And so you'll see those, and you'll see a lot more details about how things work underneath the covers. So if you want to play with something, you do not either want to destroy your own system at home, or you don't seem to have the resources, that's a great place to get started. We will talk again what a Linux container is.
What's the name of that site?
The site is called learn.openshift.com/subsystem. That /subsystem is important. Otherwise, you're going to go to OpenShift stuff, which is what we're going to be talking about next month. And it comes up with 7 different labs that you can go through. I would love to hear you, John. Tell me how they work from an accessibility perspective. There's a lot of weird iframes going on in that. And when I look at the code, I'm definitely glad I'm not using a screen reader.
Okay, so that's learn.what now? Learn.
OpenShift.com.
Oh, I see.
No problem.
/what?
Subsystem, one word.
Subsystem. Okay, gotcha. Okay, great. Thanks.
Not a problem. So we will talk about what a Linux container is, why we want to use them, and in particular how we want to use them. This demo system that you're actually seeing me present from right now is all running on Fedora Silverblue. And the reason I'm doing that is everything comes built into it. Meaning all you have to do is install that, and I have it in a VM. So all you have to do is set it up in a VM. Everything is ready to do containers out of the box. It is probably the simplest way of getting started, in my opinion. And because Silverblue comes with a nice graphical side too, it is basically just Fedora made into containers. Then you have browsing, you have everything else available that you're used to, at least if you come from the Fedora world. And of course, quite a few times I'm going to stop to do some actual demonstrations and show how things work. So I hinted at containers not being new. know we have a lot of old timers on our group, so I'm pretty sure that's not a surprise to quite a few of you. But here's a brief timeline. And to me, a lot of things are missing on this timeline that I know of. But if we look at it from just a Linux perspective or Unix perspective, we started with chroot, which I think most of us know, but we rarely use. And I did not know that actually came around in 79. I thought it came in sometime in the mid-80s, but see, get your one. And then we started doing jails. We have done, we had SE Linux, which actually makes containerization or at least isolation possible. So all of these different things as we go forward all was about isolation. How do we control what a process can do and have access to? Solaris Zones is something I think most of us also knows about. It's not necessarily a Linux thing, although there was an open Solaris that supported it. What we actually need, I think, to look at here is some of the last parts of it. So everyone should keep a note on the top up here saying Linux containers or the LXC project. That's pretty much where officially Linux, the kernel, decided or introduced officially the concept of a container. And if you ever try to use it, you will find that not only is it can do a lot of things that we take for granted now with the typical way of doing containers, but it was not easy to use. You literally have to use the same subsystem as you use for virtual machines. And your command lines became a mile long just to run them, and getting them prepared with the right file systems and so on was not an easy thing. But the kernel supported the idea of isolation, basically creating a complete new runtime within the kernel space, something we call namespaces, which are what you're seeing underneath the bottom here. So you're going to hear me a lot of time talk about user space and kernel space. And we won't be going into details of how that is defined on a kernel. If that's something we want to do, let's set up a special meeting or call for that, maybe on one of our social calls. But it's a way that the kernel looks at the world. And it's very important to understand that what we now can do is we can create a virtual mapping of what we have access to or what things are called with a namespace. So what you think is called PID 100 in one namespace may be called PID 200 in another. It's the same onto Linux, but depending on what namespace you come from, things are being called different things, or you may not even be able to see them, which is what containers take advantage of. We also see that in 2013, one of the biggest open source project successes out there came around. So it all started with a different project, which is what the .cloud Python talk is all about here, that turned out that, well, they were not successful with what they really want to do, but they have created this very interesting thing, a way of doing image layering that they thought could be used elsewhere, for something more than that. And out of that came the project Docker. And I think that we can say the rest is history. It became a humongous success because creating a container with that Docker CLI when it came out, compared to LXC, was like night and day. It was so easy. It was fast, and it just worked. It was very basic to begin with. There was a lot of security features missing that we take for granted today, but it worked. And that, what to me, was the most important time. We also noticed that almost right after that, I mean, a lot of containerization stuff started right after 13 because it became a huge success. But what I want to do here is to show that containers existed. The concept of isolation is not new. And depending on what products you've used, they have all used some level of isolation already. So going forward from that time, we see not only OpenShift coming out, we see the Container Native Cloud Foundation coming out and being established, setting up a set of standards we call the Open Container Initiative, OCI. This was signed off by all the big players, including Docker, very early on to make containerization a standard. Without that, we wouldn't be where we are today. So that standard created a call interface that everyone that implements containers today, to my knowledge, some tried not to do that early on. I do not believe they are still around in any shape or form today. And so whenever you create a container today, should be OCI compliant. And if it's OCI compliant, you can run it on any engine. And that really is a benefit to me, to everyone else using containers every day. But notice how much of this doesn't necessarily say Docker anymore. The funny thing is that Docker actually uses a lot of this stuff, like containerd is what runs Docker underneath. So this is not necessarily the whole community saying to Docker as a company, hey, we're going to go our own way. This is working with Docker and coming up with an infrastructure that is reusable and expandable across a ton of platforms. So what is a container? And well, so to me, it's very hard to define. I keep calling it isolation, and that is absolutely why we started out with containers. But often we find ourselves, when we define a container, we run them, what we define is where we don't want them isolated. Because something running in complete isolation means no network, no access to files. That's not what we want. We want some level of access, but we want that controlled. So a container on Linux basically is very isolated except for the kernel. The kernel is the only component a whole host shares with a container and that you cannot take out. Everything else, however, is up for grabs. It's very light compared to a VM. So VMs has a full OS included with everything and the kitchen sink involved just to run a web server. A container is typically just barely enough to run that web server and nothing more. A container typically works regardless of your platform. There are some exceptions, but I don't believe that any of the examples we're going to look at today even closely gets close to those examples. So I can take my Ubuntu container, run that on a RHEL system. I can run my RHEL container on an Ubuntu system. It doesn't care. And that's really one of the reasons to me that containers make such a big difference, is that when I distribute my cool stuff, I don't necessarily have to think about, well, do I need to make 5 RPM packages, 7 depth packages, and how do I get them integrated? How do I get them upstream? I just publish my container, and any one of those platforms running containers can run it. That, to me, is what gave me that aha moment of this is the future. Another part that really is interesting about containers is that not only do we package them in small packages, it means they can run pretty darn fast. So if you have a web server today on a VM and there is a failure, and let's say you have to restart the server, or you have an update and you restart the server because, well, you updated glibc and you have to reboot it. With some servers, even VMs, can take many, many minutes to reboot. If we're lucky, we can do it in less than a minute, but we're still talking maybe half a minute, 20 to 30 seconds before that system comes back up, and that's for a light server. In containers, we're typically talking to sub-seconds before that container comes back up. If it's a light load, it typically comes up right away. All the time it takes to establish a process on Linux is all it takes to get it started. And that is a huge difference. So a problem I often see is that initially a lot of people look at containers as like it's a VM. So I have a couple of slides here that tries to separate and to explain why they're different. So a VM requires a hypervisor, and a hypervisor is basically shared hardware that then gets separated into virtual components, and then you buy a special hypervisor kernel, and each VM then gets a process on that, and then each VM pretends to have full access to hardware, even though they don't. A container again has shared hardware, and now we have a shared kernel, but then everything else is separate on top of that. So notice there's no virtualization or no simulation of hardware whatsoever. Every container has full direct access to the kernel and the hardware behind it. So full speed network, storage, memory, everything else is fully available. I do not have to simulate it. And in today's world with AI and doing CUDA and all that funny stuff with video libraries. This is important. It makes it a lot easier to do with containers. So a container does isolate. Absolutely. Each VM is isolated from the other VM. But it also has a complete OS. It is very static, meaning I tell a VM that you have 10 gigs of memory. It has 10 gigs of memory. And some hypervisors, that mean that 10 gig memory is reserved and can't be used by others. In some cases, you can do a little bit of OR allocation, but not much. So you have quite a lot of overhead. And because you're repeating a lot of the OS processes, you also have running the same OS many, many, many times on the same hardware. The container doesn't do that. All I have in a container is that one process that I'm interested in. So my web server is one process, and maybe some threads underneath that, but it's just one process that I'm running. I'm not running a whole OS on top of it. And what it can do is I can share memory space. So a container can run on very little memory, and everything else that's on the system is now available for something else. And when it needs additional, we can use burst. So temporarily, it may need more memory. It gets that, and then when it's done, it gives it back to the whole system. One of the things that makes containers to me even more interesting is how do we maintain it? So when I used to be a developer many, many moons ago, getting access to a machine meant I needed to convince an admin, or more than one admin, sometimes about what it was I needed, because I did not have access to any kind of admin task, right? So if I needed X number of resources available, they had to provide it. And I had quite a few talks about, trying to convince them why I needed it. And even worse, when I then had a task to update my code, I often had to involve them because I didn't have write access to these boxes either. So if I had a new version of the code, they had to deploy it. I had to explain to them, and sometimes that was a piece of document, and we all had to write that mile long, and they never read the damn thing, right? And they had an error, and I guess they all pointed fingers at you. With containers, that's very different. I, as the developer, or the one in charge of the application, I'm in fully control of everything inside of it. I build it. I configure it. I set it up. Meaning I don't have to go through all my admin tasks to get anything of that done. So I can be 100% not only in charge, but fully own the deployment without. So I can't point fingers at the admin guys anymore, but they certainly can't point their fingers at me either. And to me as a developer, that was cool. And in the days of admin, it's nice that the developer can't point fingers at me, telling me it was me who screwed up and didn't know what Python should do or not do, and I should have known better deploying it that way. So because of that, because this whole green box here is basically in the hand of the developer, this makes it a lot faster and much more agile. One of the problems with virtual machines is that you can't really move them around that easily. Particularly not if you're going from one hypervisor, let's say from VMware to KVM, or from VirtualBox to VMware for that matter. The MAC addresses, hardware simulation, a lot of it changes, and it impacts how the VM works. And the format of the VM is different between all of these platforms. So when it comes to delivering something, we can't just say, hey, I'll set up a VM and I can just package that up and everyone can install it. You literally have to make one for each type of hypervisor out there, and then still hope and pray that they don't mess it up when they implement it. That's not the case with containers. I don't care whether it's on your laptop, whether it's in Amazon, whether it's in a data center, it's the same, exact same container, the same hash that they are all running. Think about that. I mean, to me, that is really what made the whole difference. This is why everything is containerized these days. This makes it so much better for them, those who create the content that needs to be run on machines today. It is easier for them to maintain. It is faster because they only have one thing to maintain. They don't have to make 10 different copies that all have different conditions and settings that needs to be implemented for it to work. Inside a container, we will get into this in a bit, we have something called container images. And that basically is like the physical component of what a container is. What it does, it is all layer-based. So one of the advantages is that I only have to deal with the building blocks that matter to me. So what this image here is trying to show is that if I'm responsible for the application, I can literally tell it to start from a layer that already has all the one, let's say it's a Java app. And I basically need to say, take this Java layer, or this Java container, all it has is Java and everything needed to run Java underneath it. And then I put my application. So my deployment is basically about my app, not how I set up Java in a container. And those who are very much OS specific, they may be interested in just doing the layer 1 and the base image. Setting up the base OS, it says RHEL here, and you're going to see the word RHEL and Red Hat a couple of times in this slide deck. From this perspective here, it means any OS in Linux. But I did not want to have to go through all of these slides and change the name. But just read that as a base Linux OS. So because it's all layer-based, it means that not only am I telling the developer you are in charge, but they can just be in charge of the stuff they're good at. And I can tell the OS people that they're in charge of just what they know and they're good at still. And they don't conflict. I already mentioned that. So basically what we are seeing today, and I've seen this for the last 4 or 5 years happening rapidly, is that everything is being containerized. So it means that moving workloads, we're moving them to containers. We're seeing the idea of microservices, which means very small pieces of containers. We're taking these big applications, splitting them into smaller pieces, and each piece becomes a container. And then we interconnect them. There's lots of ways of doing that. The reason that is good is that now I can scale components of the applications independently. And that's very important. If all of a sudden your site gets very, very busy, you want that site to very quickly respond. And it may be a specific components that only need more resources, not the whole app. And microservice allows that to happen. I'll quickly go by. So very basically, like a container is the compute unit we have. And this is basically saying we can run a container. We can't, from the outside, we can't specify what inside the container needs to run and what not run. A container either runs or it does not. A container comes from an image. So when we run a container, we have to say what image are we running. And then it creates a runtime image based on that. I will mention that a little bit later in a little more details of what we mean by that. And then finally, where do we get the image from? We get that from an image registry. Tons of them out there. Most probably you have already heard of Dockerfile. That was one of the first container registries out there, and that was created when Docker came around. And it still hosts a bunch of containers. Most likely you will be hitting that very soon in your own demos. But image registries exist all over the place. They are fairly easy to make on your own. So if you need, like you can do your own package repo in your own labs on your own home systems, you can do that with image registry too, so you don't have to download containers from external sites every time you want to use them. But in general, they are around to allow you to grab an image that you haven't created yourself. Once you're inside a registry, we have images are tagged. And this is one of those things that are a little hard to grab to begin with. So every image is in there with a name. That's what you see here, for instance. We have a name called frontend. But we actually, in this case, have 4 different versions of it. Actually, we may only have 3, because the 2.0 here is also the latest. So these 2 here may be the exact same image. It don't have to be, but often that's what you will see, is that when you see latest, it points to one of these existing versions. And same over here, we have a Mongo, and there's also 3 different versions, which means that I can pick which version I want to instantiate. I don't necessarily have to take the latest and greatest all the time. There may be reasons I don't want to. So once you get the tag, and every time you see a colon like this, that just means the tag you're looking at. If in most cases, if you don't specify it, whatever you're doing is going to assume you meant latest. So just before I go to the demo, I want to explain a little bit about what it is I'm going to show. So I mentioned Docker, and Docker is absolutely still around. They did have a stint where they were trying to make a corporation out of it, and now they're back to being a super duper project. The difference is that that project today is really not driving the containerization anymore. That's all OCI. So you might have noticed some announcements done by, well, things like Kubernetes, where they no longer just hint at Docker is not a required component for them to do runtime. And Kubernetes actually went one step further. They stated that they no longer will make special exceptions to make Docker work. And the secret here is that Docker is really not one what's the container. I'm going to steal my thunder from in a moment. But Docker runs all the other standardization routines already, but they have a huge market mindshare about how to use the Docker daemon. Now, I'm going to use Podman, and I'm using Podman for several reasons, but one of the things I really love about it is I do not need root to use it. That just makes it so much better. But also, everything I do with Podman, I can do with Docker by just replacing the word Podman with Docker. I mean, I can literally install Podman on a box, and Fedora is one of those I do it in, and I can alias the word Docker with Podman. So every time I write Docker, it could translate that into Podman and then runs the command, and they do the exact same thing. So don't take this as, hey, this is a complete different way. I can't use it if I want to use Docker. You still can do that. I'm also going to be using something called Silverblue in Fedora, and that's what I'm running on here. And once it's installed, Podman and everything else comes out of the box. And that's another reason I'm doing this, because it makes it very simple to use. Silverblue is basically go to the Fedora project, just say Silverblue in front of it, and you can download the ISO. And it's just like any other ISO you install from. It's darn simple to set up, and once it's set up, it just runs. It is OS tree based. If you've never heard that word before, it basically means the OS itself is a container. It means updating the OS itself is a matter of replacing the image that's on. So it keeps all the binaries in the OS, like /user, read-only. The root file system is read-only. And probably the most important thing to people who use the Fedora is that the DNF command does not exist. That's not how you update it, because it's a container. But it also means that moving backwards and forwards in versions is darn simple. And that's one of the reasons that these container-based OSs, I think, are winning foothold, particularly when you have hundreds or thousands of containers to run. That makes managing where to run them much, much easier. So let's actually do a little bit of demo here. I'm going to make this window a little bit bigger. There we go. Is that readable to everyone? Let me clear this. Oops. Hello.
Yes, it is.
Okay, good.
I can read it.
Okay, so I can do a PS. This is a normal Linux system, even though I am on Podman. I'm on Silverblue. But as I said, DNF does not exist on this box. I'm not going to go into how to manage the Silverblue, but you can read about it your own. It is not that hard to get done. If you want to customize it, it is absolutely possible. But let's keep that aside. Right? So we have a command called Podman. If I just run it, it tells me I got to tell it what it is I want to do, and that's fine. So the first thing we want to do is to ask it what's around. Now, I've actually been using this for a couple of days, a little bit more, preparing for this talk. So these are all the images it already knows about and that are already downloaded to this box. And this looks very busy. It looks very confusing the very first time you're in here. We will go in a little bit in details with some of this stuff as we go forward. But the way we get started I need to make sure this doesn't do it. Is, for instance, if I want to get a hold of Fedora and run a Fedora pod, Fedora. I say pod because I'm used to OpenShift and everything is pods there. But you use podman poll to say, give me an image. And in this case here, because of the way Silverblue is set up, it has a lot of aliases for a lot of common OSs and features, and Fedora is one of them. I basically say, give me the container called Fedora. And as you can see, it figured out what Fedora was based on this file here. And it converted it to this. All right, so it tells me that this is the registry I'm pulling from, not Docker Hub, but Fedora's. And it basically just says, give me the latest Fedora. And it went in and realized, hey, oh, I already have that. All right, you can probably see that. That was up here somewhere. See if we can, it's right there. All right, so because I just downloaded a couple of days ago, it's there. What you can see is it hasn't been changed in 2 months. In 4 weeks. It's right there. That to me is wrong. It should have been updated at least once a week because Fedora changes that often. But this is one of the things that often isn't done when Fedora releases new things. So I will find a couple of bucks on that. But now that I have that, what can I do with it? Well, again, I can do it podman images. And when you first download it, you just get that one back. Say, hey, this is all I have. But now I can run it. So if I say podman run Fedora cat etc OS release. So everyone knows what this file is. This is a common file between a lot of OS systems today that tells the OS, tells the world around it, what am I? What version am I? And it gives all kinds of links to like what logos to use. So when you have something that displays OS information graphically, it's very easy to figure out what to display. It's all in here, very easy to get a hold of. But we can use that to our advantage. So what happens if I go in and say podman for Ubuntu? It should also find it already. Yep, it's already there. And then when I do the say, let me just repeat the command and just replace Fedora with Ubuntu. I'm in the same OS, but I'm getting 2 different responses now. This, to me, is the whole power of it, is I can run whatever I want, and it doesn't have to be part of the exact version that I have. Now, there are definitely risks when we start doing this, and we might get into that if there are questions about that. But for me, this is where I will start. Now, okay, we have a container, and let me go a little bit further along here. So let's say I now want to do something cool. I want to run a web server. And one of the things I can do here is I can run the, let me see, there we go. Well, that's the one command. I want to do that. I want to, yeah. So we have a container for Apache. Now it's called HTTPD, and this is a way old one. I'm used to this, that's why I'm pulling it. There are lots of new images out there that is Apache or Nginx. I'm just pulling this as an example and something that I'm used to doing, hence I just use my own habits. Again, just because it says Red Hat doesn't mean it costs money. Everything that I'm showing here, this is a demo box. It is not logged in as me, with one exception, and I will let you know when I get to that. What I then want to do is to do a run that runs the server, and this is going to look a little complex, so I'm going to take it a little slow here. So this is the command I'm going to run. The first thing is, the last part of this we should already recognize. That's the container image that just showed above, right? That's the HTTP image. But then I have all this other stuff in front of it that looks a little bit cryptic. So the first I do is, and that may not sound something that's important, but I'm giving it a name. So later on, if I want to use it, I can use this name instead of whatever random ID the container system engine actually assigns me. So I want to know it by the name that makes sense to me. And that's what that is about. IAM tells the system that when the container is done running, to remove the image that it's running on from the system. Do not keep it around. Otherwise, I keep accumulating runtime images, and I really don't want to do that. In most cases, people, that's what you want to do. The next here tells it to detach. That means do not wait for this program to stop running once it started. Just go back to my command line, run it in background. And that's important because it's a web server. The web server in this case is not running through systemd. It is just a process. So I want to start the web server and then just put it in the background and run. The next part here, it says whatever file that is in, I'm going to show that here. I have a directory called files, and I have in files, I have a very simple file called index.html. Put that inside the container, the directory called var www.html. And this is why I'm using a container I know, because I know that that's the location that this web server inside the container expects all the Apache stuff to be on. Now, if you're on Ubuntu and it's a different, let's say it's just var www, nothing else, then that's what you use. So you need to know your container a little bit, and we'll get into how you can figure that one out. But that's how you do that. The last one tells me tells it to take the port number that inside the container that has been exposed. We'll get to that too, of 8080, and expose it to my host on 8080 so I can actually access it. All that said, I can, oops, I probably should have copied the whole command correctly. All that said, I can run that, and it now tells me, hey, I'm running. That's how fast a new web server comes up and runs. Now, if I use the word podman ps, now ps we all know, right? So the process is running. I now get this back. It's telling me there's a container running. It's been running for 14 seconds or 15 seconds. This is the name that it assigned me internally. No one remembers that, and that actually is random. Every time I run it, I get a new one. So that's not something I want to remember, but it also tells me it's calling it by my own name here, and that's important later. And it tells me that it routed all web traffic differently. So how can I use that? Well, if I now do a curl, port 8080, there's my file. Or I can, of course, go to my browser. There we go. I cannot type today. And there it is. I'm actually talking to my container, and it's responding back. But I want to show you something that probably, if you've never seen a container before, this is probably going to go, holy crap, what happened? Right. So if I do, I'm on the host right now. I'm not inside the container, and I do a PS. Notice that I'm seeing my container run here. Right? Sorry, I'm seeing my HTTP server run like any other process runs in the system. I'm on the host. This is not where the container is. I can see stuff, and I'm sort of like the super duper human. But remember, I was not even doing this. I'm just doing podman as a normal user. So a lot of magic is going on that typically would not happen. But then again, if I go inside the container, here's a new command that you haven't seen before either. And it should, yeah, there we go. So what this tells me, what this says, take a running container and execute a command. So my container I call myweb. And what I'm telling is to execute a command, make it interactive, and give me a terminal so I can actually use it, and run bash. So now I'm inside the container as a normal user would be, like I have SSH to it in some way. And now when I do a PS, note what happens. To the container, this is the whole world. This is the whole OS. Notice even more, and this is one of my first wow moments when I started containers, is this. Notice the PID. It means that it thinks the web server is running as the init container, meaning it's running as the systemd or initd or whatever it is your favorite OS calls it. and that it owns the whole box. But we know when we ran that same thing up here, that's not what it's called, right? It's a different PID altogether. So what is happening is that this idea of namespaces has tricked, quotation, the container to see the world very differently. Not only did the namespace only show what this container owns and runs, but it started the numbering system from a different number. So I no longer have to concern myself with all this other stuff up here that is part of the OS. None of that is there. It's just the web server in here, and the web server can only see itself. So even if something nasty was going to happen, it would fail because it wouldn't have access to anything just by the namespace alone. That doesn't talk about all the other security that is around this that secures it in other ways from the networking and all that. But I also want to caution a bit. I'm inside a container that is very minimalistic. A lot of the commands that you're used to are not here. So to give you an example, I want to do, I'll say DNF, for instance, or yum. It's not, oh, I can do yum. Wow, that wasn't impressive. But I can't do IP. I can't ask it what IP address is. I shouldn't be able to say, oh, I can do mount too. Oh, well, some containers have commands that they shouldn't have, and this is definitely one of those. But you will find that inside containers, this directory here are typically very small compare. And I'm very surprised to see that this has almost 600 files. This is definitely not a minimal container. That makes debugging easy because most of my commands are going to be here. So I can go around tricking things out. But again, I'm in a container that is going to run a web server. Why would I need to be able to do the Zcat or a zip or anything else? There are situations where some of that may be needed, but it is rare. So often what we find is when we create these containers, and this is an old one, that most of this stuff in here disappears. We do not need it, and it makes the container image so much smaller when we do it. But it also makes debugging a little bit harder, except it is actually not that hard to get around. So remember when we did the run here, right? I mapped a local file system to my container file system. I can do that with any file system. So I can actually map my local user bin to the containers user bin. Presto, I have access to all the binaries that my machine has. So we can cheat in a lot of interesting ways to actually get access to commands. And there are other ways of cheating too. So just because they minimalize what's in the container doesn't mean we actually have to deal with those kind of situations. And yeah, okay, so I've actually gone through all the demo stuff that I wanted to do here. Oh, we need to stop the container too. So again, so we have a container running. To stop the container, well, use the command stop. And now it's gone. So now if I do apartment PS, it's gone. And it should also be gone there. Yep, it's there too. We're gone there too. Notice that the two ones that I did before, the little cats, they're still around. And that's why, because I didn't use the IM when I ran those. So these are actually still existing, and I'll get to, when I get into the little more deep dive of what a container image is, I'll explain what's going on. But technically, what we have done here is a very hello world-ish kind of introduction to how to use containers. It's that simple. A lot of times when you go to talks or when you read about containers, a lot of technical mumbo jumbo is being given you about how things works behind the scene, and it is absolutely fascinating stuff. But to just get started with them, you really don't need to start there. You start with run, pull, whatever, and it just works. Now, at least for me, what happens very quickly is that you want to know how it works. And you can use that to advantage later on. And that's where you need some of that more technical mumbo jumbo going on. A short thing before I go back to it, notice the names in these. This is why I gave the R container my own name. It will come up with the funniest names ever, and just give them random names. And that can be fun. You can have fun all day just looking at all these combination of words that it has and just puts them together and just enjoy yourself. But I prefer to give my container my own name so I know how to refer to them later. I don't care. Let's do this. Okay, so that was the basic demo. Let's look a little bit more about what these container images are about, and then we'll talk about the registries, and then I'll actually show you how to use those registries and images ourselves. Right. So the container image is, it's a lot of things. But it starts with a base image, right? So remember, I had that image where we showed the different layers. And we start with what we call a base image. That base image is basically the core components of what's needed to run stuff. It's the libraries. It's the basic packages that you need in there. It's basically what makes enough to actually get a prompt or something that can run a piece of code. Now, what's in that layer is up to you. It doesn't have to be a lot. I mean, BusyBox doesn't take up any space at all because it has the bare necessity to just run it. But it also because BusyBox doesn't do anything. If you need BusyBox to do stuff, then you need to all of a sudden start adding a lot of stuff just to support it, like SSL or firewalls or some IP management and all that stuff. So if you look at a container image, we have multiple layers. They all refer to each other. And the base image are defined by, basically, we have an image index. So basically, we create a binary image initially as a base image. Typically, we will start with a tuple. Someone says, here are all the basic binaries from glibc to all my core libraries, all in the tuple. And we basically tell the container command to build a container based using that binary image. From then on, we say build on this base image, build on that base image, and notice we can use the same base image for a lot of different containers. So because this is all based on that open container initiative that is out there, and it's all standardized, these images are defined the same way regardless of your platform. So there is a manifest JSON that tells it what are the layers that are dependent. How do we actually combine with the different layers and stuff like that that you can specify. Now, it happens automatically when you use the CLI, but if you want to, these files are available for you to actually view and even manipulate if you want to. I won't really go into details in this talk. Just know that while it might look like magic, it's really not magic. There's some very basic files around that tells the system what to do. But let's look at some of the technology what we need to look at to get things in. So one of the issues to me has been, how do we get started? Right. And we could start with statically stuff. Right? We can start putting in things like GCC that is all statically linked by itself. And we can put in other things like whatever it takes for the OS. It could be an interpreter, but the interpreter needs other stuff, right? So what can run by itself? Well, only statically linked stuff, binary code can run by itself. And so typically we will have, in all containers, we will definitely have glibc and probably either create that using GCC or put GCC inside the container. But at the very least, we'll take the artifact that GCC creates and put all of that stuff into that initial base layer. But we also have dependencies. Right? Very rarely do we have a library or a binary that stands by itself. We have dynamic loading all over the place. We often don't think about it, but when we start creating a container, we have to be aware of all those dependencies has to be inside the wall of that container. So we need to be sure we are packaging them all. And that's often where we had that conflict between the developers and operators before, like where the developers assumed that, of course, this library would be on the OS. Who would ever run an OS without this library in this version, right? And never to specify it. In this case here, it has to be inside the container. Otherwise, nothing will work. And the developer cannot claim it works on my PC because if it's not inside the container, it doesn't exist. One of the things is when we have libraries, like dynamic libraries, there's a subsystem like the LD subsystem that has to exist for the kernel to know how to load them. So all of a sudden, it's not alone just to have the statically linked libraries anymore, binaries, sorry. We also have to have the tools available that the OS, Linux uses to load things. So there are some technical dependencies we have to ensure. So if you build your own container from scratch, this is stuff you need to know. Once you have that, we have apt, we have yum, we have DNF, we have all these different package modules that can be used to grab other dependencies in. So if, for instance, if I want to do, again, a web server, that RPM comes with a ton of dependencies that I need to get in. And luckily, RPM or yum will help me to determine what that is. But it now also means that I'm becoming dependent on my distribution. And that may not be a bad thing, because as me, someone who's more familiar with the Fedora side of it, having a container that inside of it looks like Fedora makes it easier for me to figure it out. But it doesn't mean I can't figure out something that is made for Ubuntu. It's just I need to look in different locations to find things. We have for other languages, like Python or Node.js and all that, there's other tooling that can be used to figure out what are the dependencies that I need to do. And often what we will have is that it's going to be a file created by the developer that says this code depends on all these libraries. And that file is then used to compile, put everything together automatically. So it's not like someone manually goes in and picks all the libraries to download them. It all happens by running pip or npm or something else, and it will use that metadata file to download it all. But that's another way we get our dependencies into a container. So by the end, we have put everything together. We have a base, and then we can start putting in our code late at the very last step. But as you can see, what happens is that each of these containers, every time there's a change, let's say library changes, let's say the version of glibc changes, I'm creating a new layer. I'm not updating the old one. It's very important to know that once the layer is built, it never changes again. And that goes on even in the container world. So once a container is running, it doesn't change. And we will soon see why that makes a difference in a moment. But just think of it as we create change sets by creating layers. So every layer we create, or every image we create, is a new change. And it could just replace or augment an old layer. But every time I have a change, I build a new layer, or most people just see it as a new image. Very few look at the actual layers, although later days we have all tried to optimize and make things much faster, and layers are beginning to really matter. And so we're starting to look at it a lot more. But from a basic from a basic use of a container, you just build a new container every time you have a change. Have a new version of the code. You want to get the latest versions down from your distribution of whatever libraries you're using, you build a new image. So because they're change sets, we have those tags that you saw earlier, we can now refer to the different versions, to the different builds using these tags. So I can still tell that, hey, this code depends on version 4 or version 5, and I can build them independently even on the same system. They can all be called MySQL or MongoDB or Apache or whatever, and have them in different versions, and I may be using multiple versions at the same time on the same box. And again, try that without virtualization, but if you do virtualization, then you can do that. We have full OSs on top of it. This allows it to run with the same kernel, no overhead, no nothing. So one of the things that can be a little bit of a challenge initially. So when I do a VM today, one of the last things I do is, once I've done all the standard installation, I now start configuring the VM to do my stuff, right? So I want to create my website with my own. So I start uploading style sheets. I start configuring the web server to activate the right PHP version, and I do all kinds of customization. That we do not want in the container. That makes the containers not only specialized, but it may not even make it portable. You don't set up a host name. You should never set up an IP address. It doesn't exist for that matter. In particular, you don't want to put content in there that could be conceived as configuration data. So all of that typically we see coming outside as a user option. that is injected into container when we run it is not part of the image. That takes some getting used to, but it's not that hard to get to. But again, look at each layer as we see them. Again, as a part of if you look at it as a timeline, you have different versions of it. And within each version, there may be a latest version, right? There might be a 4.1, and then you can have 4.1.1, 4.1.2, 4.1.3, and you may only want the latest of 4.1, but you don't want 4.2 or 5 or something else that is out there. So be careful when you pick those, but because your configuration options are in a separate box, it doesn't matter to that configuration option what version you're using. And that's pretty darn important. Do not repeat yourself. It's kind of important too. So when we build images, if the base image you're using already has a feature, you don't need to reinstall it again. Particularly, you should not be overwriting it. So you should not, when you build your container, put your own glibc version inside of it as the very last. If glibc, which it should be, is in the base container, let the base container own that. Because if you overwrite that, then you might become non-compliant very, very fast. Meaning that when the base layer changes because there's an update, let's say the security thing coming out, and they make a new version because your image later on puts a new version on top of it, or a different version, you're overwriting that change. We don't want to do that. It also makes the image much larger. So for that reason alone, we don't want to do this. But you should just put in the stuff that you need, nothing else. And using all these dependency resolutions helps you only put in what is different, because it will know what else is in the system. I know it says OpenShift here, and we will get to that next month for how to do this. But there's a lot of automation, and OpenShift is not the only one doing that. But this is part of what Container Engines helps with, is to figure out this whole hierarchy of images and how they belong together and how to optimize things running inside this hierarchy. And even more important in my world, how do we keep things up to date? How do we make sure that we are not using an outdated version of a particular library when we have it in this kind of an image? That is definitely a duplicate. I'm going to skip that one. So, container registry. So I've talked about images and what's inside of them, but we're going to keep them somewhere to be able to actually access them. And a container registry is it's almost like a Yum repository like you use today, right? It's a dep file. It is a server that responds with an API that allows you to find, to retrieve images, and to push images back. So we have something called pull. You've already seen that. And the opposite to pull is called push. So that's my way of sending my image that I have locally and to get stored on the server. That's very different from RPMs that send, or deps. They're always read-only to us, right? If I want to update one of those, I have to sort of find a back door onto the server that they're hosted on, and then inject my files there, and then update the index and all that, so everything can find it. With containers, it is pretty much a given that if you get access with an account, you can push your own images. You can't overwrite other people's images. That will kind of be silly. But you have your own area, you can push your own images up, and if you get enough writes, you can then make that image like a global, easily findable image that everyone has access to. So it's where we share data, share images. It's where we can actually get data about containers so we know how to use them, et cetera, et cetera, et cetera. So what the registry does underneath the cover is to take all these layers and find an optimal way of storing them. I will try not to go too deep into this, but this is actually, to me, a very fascinating area, because not only do we need to be able to store these effectively, but we also need to be able to make sure that we don't have bad code out there. And bad code is not necessarily code that is, purposely full of backdoors and stuff like that. That's definitely one of them, but it's also code that is old, that hasn't been updated for a while. And because we have all these layers, we need to be able to scan each layer to find out if any of these layers have known issues. So a lot of these registries, Cray is mentioned here, but you will find even that on Docker Hub today, will dissect the layers that it's storing and scan them individually to see what's inside of them, to see if there's any known vulnerabilities that needs to be taken care of. And in some cases, it may be so bad that it will refuse to allow you to use it. There's other ways of looking at it. There will usually be some kind of score set up so you can just look at it as without knowing how they did it to see, how good is this container image? Is it new enough that you can use it, or should you be a little bit cautious about using it? So a lot of times the problem we have is, where do we get our container from? I can go in and search, and I'll show that in my next demo very quickly and get a list of ton of containers that exist. The same container existing in a ton of different registries. That's what I wanted to say. And which one to use? Which one can I trust? If someone makes a registry out there and just says, well, I have what you need, I can do the latest WordPress and just come download my stuff. How do I know that the content of that doesn't contain weird stuff that I shouldn't be using? And it comes down to trust. So a lot of us starts by basically defining a registry, a source that we trust. It's sort of like when you run, in my case, when I run Fedora, I trust the Fedora server is implicit in that case. I know the process. I know if something is signed with a Fedora key, I can trust it. That said, doesn't mean I don't have third-party repos, but I have a different process of verifying that that's okay before I will trust those. The same happens with container repositories. I can trust the source I have. The problem is that over time, things change. And as you saw, I pulled down a very old version of Apache. It had all kinds of stupid stuff in it that shouldn't be there. It shouldn't be there anymore. It should definitely have been updated a long time ago. And in that case, over time, things change too, and goes from being good to being bad. So even though the thing that I have might be signed by those who created it as saying this is the true thing and it comes from a trusted source, over time, none of that is enough. Knowing what's inside the container is basically something that happens all the time. You need to keep reevaluating it. And sort of like you do with a server today, you keep having to update it, whatever schedule you have, but it has to keep being updated to stay up to date and not being vulnerable to stuff. So pushing and pulling, I already mentioned what that is. So I just want to show the command again. So in this case here, the pull that you saw, if I replace the pull with a push, that's all I need to do to push this image back. But as you can see, there's a registry, there's a container, and this could be, in this case, there could be a group of containers. So this could be your namespace. It could be your organization name or something like that. It could be the project you're on that has its own area for own containers. Then there's the repo, and then there's the tag. This is typically how you will find most containers in this kind of format. Hostname, a group, organization, or something like that, and then a container. In some cases, this is omitted. And that's simply because it might be something very popular and everyone pulls it down by name only, and it just pulls it from the latest one. The last thing is, and this is, I got bunch, not only slides about this, but I don't want to go into too much. We are running out of time already. Because we have more than one layer, the way Linux deals with this is once you're running them, it puts the layers on top of each other. Right? So it starts with a base layer, puts another layer on top of it, another layer on top of that, and one layer on top of that again. And it uses something called a graph driver, which in current versions are implemented using something called overlay 2. And it means that the OS loads every layer as if it was either into memory or at least onto the disk. And all the data in each layer are loaded together, which means that if you have the same stuff in all of them, you're loading in more than once. You don't want to do that. But it also means that when you do an access to a file, it starts from the top, meaning not the base, but the top layer, looks for the file there. If it doesn't find it there, it goes to the next one, to the next one, to the next one, to the next one. Now, it has some optimization, so it knows right away when you don't have the file. It doesn't have to do it that way, but logically, that's what it does. And that means that if you define a file that is on a base layer later on, in your layer, then it's going to be your file it retrieves, not what's in the base layer. So you have full control over that. The OLA2 file system deals with all of this. But when we go in and look at how the images look on your box, it's important to understand that these layers are individually, because that's the way you're going to see them on the storage system. So let's take a look again on how we actually do a little bit of imagery and stuff like that. So let me do a clear again. So let's do an interesting thing. Let's actually take a look at a WordPress image. And I'm going to do this. So let's say I want to know, wait a minute, can I do this? Before I do this, so let's say what WordPress stuff is out there. Let's ask that first. And as you can see, there's a billion WordPresses out there. And it always comes back to me to which one can I trust, which one can I not. And in this case here, I'm going to use this first one on the CentOS side. Again, that's what I'm familiar with. Doesn't mean any of these are bad. What I have found is, because everyone makes their own WordPress, it's very hard to make sure that what you get is a maintained version. Always try to, and Docker does this. This is how Docker Hub makes it into some kind of official verified version. No, I can't do that here. Let me make this a little bit smaller so it's easier. Notice that a lot of people have voted it up, which means this is sort of the official version. These are all individuals or special versions of WordPress that has been made available. And you probably only want to go to the top one. And I'm going to use the CentOS. But let's say I want to know what the heck is going on with that container. What is it? How does it work? I'm going to use an inspect, but I don't even have to pull it, meaning I don't have to put it in my box to know it. So I have a command called Scopio. I will not have a lot of time for Scopio today, but Scopio allows me to manipulate remote containers. And it allows me to say, take the container in this repository over there, put it over here, or take this container, put it on my own file system so I can inspect it. It basically allows me to do what CPIO does, or DD does for normal files. It allows me to really get insight and manipulate stuff going on. But it also has this, hey, let me actually see what this is all about. So it gives me, and to me, this is a summary. I'm going to show in a moment why this is a summary, okay? But it tells me about what this is about. So it allows me to see the labels that people attach. And often this tells me about the licensing. It tells me who owns it, who maintains it, and so on. It also tells me there's actually 5 layers. And I could use these IDs to retrieve and inspect those layers individually, but I don't have to. And it tells me that the container defines an environment variable called path when it runs that uses these directories. It also gives me a little bit about the architecture, but that's about it. It actually doesn't even show my entry point. Now, let's actually check this container, and I will download it to my box. Be here already? No, it's not. Let's hope it happens fast. I did some cleanup, and I guess I cleaned up too much. So we got the first one already, and then it's downloading the other images and putting it all together for me. So this is the process that normally happens when you pull an image that you don't have already. Give it a couple of seconds. So while I'm not speaking, any questions so far? Everyone has been so quiet.
Well, I have a question. Again, so to get a valid container, in other words, you just have to trust the repository of who's giving it to you, basically.
Trust but verify. But yeah,
Right.
it will start by you trusting the source, yes, and make sure that you sign for it and all that. Yep.
Yeah, all that good stuff. Right, right. And the layers are actually separate files on your file system. You'll see the layers as separate files.
Yes.
You know, I get you, yeah, because I was fooling around with Docker and saw some of it, and it was really hard to build. I was trying to build Docker for FreeSwitch, and and it was quite difficult to get all the pieces correct. So it could be tricky, and then to expose all the right stuff and so on. You know.
So definitely on the getting started side, you really don't have to concern yourself with where the images are stored and what they look like and all that. You can just look at it from the command line that I'm doing here, and that's really what matters. Everything else is for the advanced using. It comes later on. Once you're going behind the basics, you will definitely want to know some more stuff. Anyway, I wanted to show, now that it's downloaded, let me do an inspect now that it's on my local system. And things are going to look very different. Let me do a less here because it's going to be big. So the repository knows a kind of like a summary. This gives me every metadata piece that is inside the container and allows me to actually see what's going on. So notice that I'm told where it's coming from, blah, 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 but all this configuration stuff here, I really didn't see before. So this is what tells the, in this case, the container engine what to do. So it tells me that if I want to run this, the container exposes port 80. It uses this path, which we were told before, and this is how it runs the container when I say run. It has these labels. We saw those earlier, but now it also shows me what is the graph driver it's using. Where does it get the data from? In this case here, this is where I put all the files. If you really want to know how it's constructed, this is where I would go. Here, all the stuff that makes up this directory, this container itself. It gives me more information about these layers, what kind of metadata is around. It even gives me a short history about how this was created. That's also part of the metadata and how it was put together. So I get a lot of data, and we're gonna, once we get into building our own container, some of this stuff is stuff we actually have to specify ourselves, otherwise it wouldn't make any sense. But I will hold on to explaining why we need to expose posts until we get to that. So we can do a search, we can do a pull, and finally what I want to do is I also want to do, see if I do what Podman images here. So we will see that I have my WordPress down here, right? What I need to do is I want to get this ready. Oh, wait a minute. I'm going to cheat a bit. So first thing I need to do is I want to go to this guy here. As you could probably see, I have a registry. I have my own access to create. Anyone can get that. You just need to sign in with an account. And you can then push and pull container images. And now that Docker limits the number of pulls and pulls, I see, I mean, Creo is not the only place people are going, but a lot of projects seems to be going to non-Docker stuff, because I cannot tell you how many of my old demos that use Docker are failing now, because it may be running on in a data center somewhere, and there's a limit to how many times these IPs can reach out to Docker before they limit you, and we keep running into that. So we are moving, I'm definitely moving my containers off to another non-Docker IO, non-Docker hub, so I don't have that limit. Now I still have stuff there, but not as much as I used to. But what I want to do is I want to change this around to basically say, I want to be able to take this container here that I just downloaded. I want to put that into my own registry. How would I do that? The first thing I need to do is to log in. And because I need to use a password for that, and this is a public demo, I'm just going to say Podman login, and it's, oops. Should see. Oh, login Podman. Oh, okay. And it's going to do the command for me without showing it. But what it basically did was saying Podman login, and then a user, blah, and a password, blah, Creo. And of course, this, if I did this, it wouldn't succeed. There's no user and password called blah. But that's how you log into a registry server somewhere. And that means that when I now continue and I do stuff with that registry, it is going to use my ID against that server. So the first thing I have to do is to retag the image. Right? So I will basically say tag, and because I am lazy and cannot write anything, so I will say take this. I'm so lazy I couldn't even hit the right key. Right, so I'll take this, and then I will say tag it with Creo, put it into my library, and I will call it WordPress. Okay, I'll call it 1. I don't care. No, say latest. Doesn't really matter here. Right. Didn't seem to do anything. Now, if I do apartment images again, you can now see that it appears down here. But notice it's the same image. The ID is the actual definition of the container, and I can call it whatever I want. It still points to the same image. It's kind of like an inode on the file system. The inode is what the actual file is, and the access rights and all that stuff. The name is basically just a pointer, and the same happens here. But because I now have authenticated, and because I have it tagged, I can say podman push WordPress latest, and it's now pushing it. If it worked, I've seen that happen before. Okay, I know what's going on. I don't want to sign on to Quay and tell it that it has access, so let me just do the other one that I prepared earlier. Notice I have a similar one from yesterday. You can't see that date. That's the container image. I will use that instead as the example. That should work. Happens when you do demos. So as you can see, it was already uploaded, and that's why I really wanted to retest it. But what it's telling me is that for some reason, it's not allowing me to create a new repository, a new container image, even though I'm logged in. And I've seen that happen before. Try this again, but I doubt it's going to work the second time. Typically, when it doesn't work the first time, it doesn't work the second time. Oh, no, it works. Oh, fun. Anyway, I may not let this work because, but as you can see, it's the same 4 images we saw earlier on being downloaded. Now they're being pushed. And once they're pushed, now I can pull it from any other machine around the world if I make this repository public and get these exact same bits. It's that simple, right? It's much more simpler than getting RPMs published. Once you have a server out there, and you can even build your own on your local app. You can go to Amazon and use their container registry, or you can use Google's container registry, or I mean, pretty much every provider out there seems to have one these days, including Docker, of course. And plug your container in that, and when you tell friends or colleagues where you put your code, you just give them the URL to where you put it, and they can download it and go on from there. It doesn't take more than these basic commands. Now, I had initially planned to go a little bit deeper with some of the things that Podman, in particular Scopy, allows me to do is to grab all this container image content and inspect it and actually manipulate it. We won't have time for that, so I'm going to leave that, but let me know. I will definitely be happy to come in and do I will call a container deep dive if we need to explain how that works. But this is the basic stuff. We all saw how we got a container. This is the way I will take an existing container and push it up. The next demo that I'll do after the next couple of slides is about how I built my containers. And those are the basic steps that you need in order to do containers yourself. That's it. It sounds like a lot of things. There's a ton of commands that we haven't looked at yet that may sound more complex than they really are. So to me, when Docker came out 7 years ago and had these basic commands in it from the get-go, that was like, holy crap. It made it that simple. Compared to a command line that probably was 200 to more characters long every time you wanted to run a LXC command, it's night and day. The whole idea of the layered images won me over, basically, to say this was the genius behind what Docker started out by doing. I'm very, very grateful that we had people like that inventive and coming up with new ideas. So let's go on to the last step here. So I'm going to talk a little bit about where we run the containers. We call them container hosts. So as you saw here, I'm using Silverblue as my container host. Typically, we don't really want to create production containers running on a single machine. Because if that single machine goes away, then everything is gone, right? We also don't want to put all the dependencies in one box. Typically, when we had an application needing a database, we would have them on separate machines, better management, and all that stuff. So the host actually matters. The first thing that matters here is, and I know this is a common thing, and I understand what people are trying to say when they say it, but it does not mean it's correct. Containers don't run on Docker. They're not Docker containers. And the reason for that is Docker doesn't do anything other than tell the container engine behind the scene to run the container. That's exactly what Podman does too. They do it in different ways, but in essence, none of them run containers. Like, I mean, my Podman exits after the container has been started. It doesn't run anything. It's not even in the PS that you saw earlier when the container is running. It's gone. Docker has a daemon, and you can see that, but the daemon doesn't necessarily own your containers either. And that's sort of on purpose, because if the daemon dies, you don't want to kill all your containers. But in essence, a container is just a process, or it can be a set of processes. And they run in the Linux kernel. That's all they depend on. Everything else is trickery about how that process is isolated on the host. So we don't have to consider our host like a Docker box that needs to be set up with all kinds of Docker specifics to make it work. Now we can do that. And Docker has some great engine tooling, and particularly workstation tooling, that does local development of containers even easier. That's fine, but that's not my runtime box. That's typically my development box. So there's really nothing in the kernel that says this is a container versus this is a process. This is, I guess, a public secret by now, but one of the things that systemd has changed, at least in the Fedora and RHEL world, is that whenever we have services running, we are actually running every service in a container. So we are using things like SE Linux, we are using things like C groups and namespaces. That's what makes up containerization. Now, we don't use container images, but we can isolate without them. Now, a lot of the processes you see today are not 100% isolated, but they're still using the same technology. And that's the exact same technology used when we run a container this way to the kernel. It sees a normal process with a little bit of special security around it. There's really nothing else to it. The container engine basically is responsible for converting the human way of looking at it into what the container or the kernel knows. Once it's running, it's just a normal process. And what we have is a way of doing some CLI calls or so on to effectively just send commands to a subsystem underneath it. And we have a couple of them, one called runc that Podman is using, that literally is the one sending a command to the kernel that says run this process with all these parameters. And they can be mile long still, but I didn't have to write that. It used all the metadata and put it together for me. Docker does the exact same trick. So it's, in the end, they're both the same thing to the Linux kernel. So the container engine is there to make things easier. So you just saw some examples of this, right? You saw me doing container images. You saw me, you haven't seen me build one yet, but you see me use them. I can call registry servers. I can run things. I can build them. I can do a ton of stuff from a single CLI. And all that is driven behind the scene. And in this case here, as you can see, this might be a little bit small print for you, but the OCI runtime, the the open container interface is runC. And it doesn't really matter which engine you're using on front of it. It all uses runC. And what it does is allow you to basically inject configurations, setups, optimization, all kinds of funny stuff that that engine actually can help define. So it sets up the parameters you run into OCI. So the big question really becomes, are you OCI compliant? And I think I mentioned that earlier. Pretty much everything is these days. Docker is, Podman is, and I will not get into CRI-O until next month, but CRI-O is the runtime version of what Podman is, but it's meant to just run, and it is also compliant with Kubernetes and fulfills the Kubernetes standards. So CRI-O is what is being used in bigger platforms today. Podman can still be used, but it's not used for, for big scalable stuff. But anyway, from this perspective, both Podman and CRI-O runs the container pretty much using the runC and same way of doing that. Okay, sorry. Another way of looking at this is, instead of looking at the engine as a lot of processes, your host is your engine. And for that reason, basically, is once you've installed the basic components like Podman or even Docker, your host is ready to run stuff. And now it's your host and not all the bits and pieces of it that you really care about. And the cool thing is that the API, once it's defined, it doesn't really matter where that host is. It can run it remotely too. We might not necessarily want to do that all remote, particularly during development. We want it all local, but it can be done remotely too. So all these components in here are basically what you find in the container host itself. Everything in the container host is all tested and verified together, and this is often why you see special distributions for that. You may have noticed the word up here called Red Hat CoreOS. I actually don't like them calling it that. It should be called Red CoreOS, but that's a different matter. So CoreOS is a container-based, container-optimized version of RHEL that, just like Silverblue, is made to only run containers and nothing else. And it is optimized with all these things in mind. Now, can I do it without it? Sure, but it doesn't necessarily mean that I'm going to get updates in synchronization that ensures that when my runC is updated, that is updated in conjunction with whatever is required on the kernel side. And the container engines are, because these components are very key for them to work. So without this whole stack working 100%, you may run into trouble. And hence, these are all updated together on a container host. But I can simulate them easily on any host. It's just a matter of how do we manage, how do we test it, and update it. So let's get to the more fun stuff. So we talked a little bit about what containers are, where to find them, but let's try to build some on ourselves. I am pretty sure everyone has heard the word Dockerfile. The Dockerfile is the traditional, and it's pretty much also the de facto standard for most container builds out there today. It's a text file that, it's not programming, it basically has a set of commands in it that tells it what needs to be in the container and how to build it. Now, that can be quite complex. It can run all kinds of code for you and do things that, typically you wouldn't expect. But it is literally just a set of metadata that says, this is what my container is supposed to have inside of it, go build it. And so we have a couple of common keywords, and you're going to see them in my demo, but let me just go very quickly through them. Every container you build has to have a from. So it basically says, what is my base image? Where do I build from? What is the core that I need to start from before I start doing my own stuff? Then there's a run command that tells it to run a command, and it could be, let's say, yum install, it could be run this shell script, or run this compile, or something else like that. But it basically tells the build system to, inside the container, run a command that will produce results that then also becomes part of the container. Entry point is where we tell the container image, when someone says run image, like run the container, this is the command that we want to be run when the container is running. Copy is a way of telling it, take this local file and copy it into the container. It could be you have built something locally. It could be that you have a ton of, let's say, images for your web server that you want to be sure always is there. Copy them in. There's all kinds of ways of why you want to need copy. Maintainer is more or less just there's also a description, but it's basically just a little bit of metadata that says who you are, and that becomes visible to people who are searching your container image, and that could be part of what you use for trust building. Although it's just a meta tag, anyone can write anything. You can write Santa Claus, doesn't care. env sets up a set of environment variables that should be defined automatically when the container starts. The working directory or work dir is where when the container runs, what is the default, what is the directory it starts in? Often that's the same directory all the way through. We don't change it once it's running, but it could be changed. But it's basically just your login directory that you would have when you log on as a normal user. And the final one is exposed. You saw that in the metadata a little bit earlier. So when a container runs, we typically need to communicate with it in some way. And that's most likely done through network. It doesn't have to be, but that's the most typical way of sending commands. Like a database server listens on a port for database commands. A web server listens on a port for web commands, and so on. And we need to tell the container which port to expose outside the container. Basically punch a hole in the firewall, so to speak. Those are not the same as what is on the host. So I can have 10 containers all saying they are using port 80. They will all work. They will not be in conflict. I need, when I run the container, to tell it what to do. That was that -v command you saw earlier, what to do with that port. There are a few more than these, but these are the main highlights that I would use when you get started. And most likely, you might only need from run and entry point for most of your stuff, in particular when you're just starting out. Here's an example of a Dockerfile. I stole this from Docker itself, so I did not write this. I was running out of time last night. So anyway, this is literally all you need for a basic container. For that purpose, I really like this example. So it says, I start with a base image called Nginx. I'm saying the author, I'm creating an environment variable called author that is set to Docker. And the cool thing is they're using it later. I thought that was actually nice. I start my working directory when I log in is that the process needs to be in this directory. I'm not sure why they do that. This again is a demo. And then they do something that is a little bit odd to me, but they copy a local file, hello Docker, into the HTML directory. You can absolutely do that. That does work. It makes it part of the image. It's not always done this way, but it is absolutely a supported way of doing it. And finally, it says whenever this is run, this is what you need to do. So here's a command. It says go to this directory, even though it's been told to be there already. It changes in this file. It changes the word Docker to whatever author was up here, which is also Docker. So it's going to be the same. And makes it into index.html, because remember it says hello Docker here, so it changes the name of it, and then it runs Nginx at the very last thing without a daemon. So when I run this, it basically starts an Nginx server after just manipulating that little file to show. So what this shows you is that this command can be kind of complex. You can, I mean, it's just a command like anything else, but every time you do a run and a CMD and so on, a CMD is a single command, but every time you do a run in here, let's say a DNF install, a yum install, apt-get install, it creates a new layer. It's important to know that. So you will often find a single run and a long compound command that says run this command, and then there's two ands, and then another command, and then two ands. So to Docker the engine, it is a one single big command that it runs and creates one layer. But other than that, it's that simple. We have another example here. Oh, yeah, I'm repeating myself here. So you can see here we use run. So this starts from Alpine, and it uses the apt kit, and it adds an update for pip. Then it uses pip to installs that up, so you can actually do some dependencies with pip, copies in some special files for it. You see we can put in comments here to make it easier to understand. Copies in my application, copies in some templates, tells it to expose port 5000, and then finally says when this container is run, start Python and start my app that I uploaded. And every time it does this this run, it creates a new layer that is created. So each layer may not be very big, but it does create a new layer. Every container that needs network access needs to have whatever port the container listens to exposed. Again, that is not the same as the host port. And yep. And then often you have a directory like a building directory, and then you have all your local files in there. Okay, so Builder is the last of the three amigos that I want to mention shortly. I will probably not show too much of it, but I will mention it briefly here. So Builder is a way of you can still use Dockerfile. It absolutely has the bot, the Builder bot that does a bot fulfills the whole idea of the Dockerfile. So you can use all the stuff, but it adds an additional thing to that. And that means I can split everything up in local commands. So I can run tests and see what happens without having to start all over my Dockerfile every time I have a change. So I can run, say, first I want my copy done, then I want to see what happened, then I want to do my run, I want to see what happened, then I want to do my from and see what happened. So it allows a lot better insight, at least in my opinion, to figuring out what is the best way of building my container than anything else.
Well, what's the name of that?
Builder. The fun we have is that the lead engineer that did all the container stuff at Red Hat when they came up with this idea is from Boston, and he has a heavily Boston accent, and the Dan Wallace is a very funny guy, and people like to make fun of him, and because they like to make fun of it, the engineer who came up with the idea for Builder basically named it in a Boston accent, because they're going to build some containers. So that stuck. It's still there. So it's built with AH after it.
Oh my.
Yeah. So that's the fun little pun to Dan Walsh, but he is taking it with and owns the name now. So yep. Anyway, so here's an example of using Builder. And my initial idea was to do this, but again, looking at the time here, going, I'm running out of time, so I don't want to do this. Notice that each command is separate. It's not a big file anymore. I can run things very simple all the way through. And the only difference is that I need to do the commit when I'm all done and tell it where to put the image. But it means that I can inspect and see things happening without having to basically run the image and try to figure out why did this happen, at what time did it fail, blah, blah, blah. What I like about this example too is it shows you how to compile code. Right? So in this case here, it actually puts in a piece of C code and makes sure that all the C compile stuff is installed, and then it does the make install. Really, the container doesn't change what we can do with Linux. It's still Linux inside of it. It's pretty darn important to remember that. So whatever you can do in Linux, you can do in a container. It's just a matter of how do we create that image. Now try this with LXC and then tell me how easy it was to get there. That's what that image, whole thing about images changed for us. The last thing I want to mention about Builder is I can take an existing container and I can mount the damn thing in my local directory. So I can see the intro. I don't have to run anything. And I can actually inspect every little piece of what is going on if I need to. And even more fun, I can modify that system and commit it back, and now those changes are in my container. It makes it darn flexible, to be honest. And I wrote the commands down here to how we would do that. Again, we will do a mount, and then we can go into that. We can install whatever we want, and then we can do the commit. Anyway, yes. To me, Builder is a better way, but it's not the only way. And the Dockerfile is not going to go away. Dockerfile makes distribution of source repositories fairly simple. So I don't see that going away. But from a debugging and a development perspective, this is a better tool. Containers are immutable. I think I mentioned that a couple of times. But to be very frank, a container is built to not change. When you have created a container, you know that ID, that hash you see, makes it unique. Every time there is a change, that hash changes. It's a new image. That means that when you run the container, while user and a few other directories may be read-only, it is gonna look like it is read-write. And it is going to look like it's read-write because every time you run the container, a new copy on write layer is created on top of everything that you're writing to. But that's a temporary layer. So the moment the container stops, particularly if you're using the RM parameter that I'm doing, that layer is deleted. And meaning all those temporary changes, and that could most likely just be temporary files, are lost, are not retrievable. Which means next time I run the container, I am starting from the exact same point I was last time. No differences. And to me, that is a huge advantage. I don't run the risk that some file changes the way my system starts up. And then hence after reboot, nothing works. I've been there, done that, I don't like that. If you do not use the RM, one of the advantages is that you can go back into the container and you can actually use the commit to say whatever state this container is in right now, I want to save. That can save you, but now you've lost the track of what it is that built that container, and it might not be the best solution ever, but it is possible. So the assumption should always be that they are mutable, they don't change, and if you need them to change, you create a new container. And often, if it's just a layer, it keeps all the base layers and just changes that top layer. So if it's just a small file in one layer, that change is very quick to be done. Last but not least, what should not be in our container is configuration. IP addresses, host names, certificates, what is the service ID, security, like what is the usernames defined, all that stuff should never, ever, ever be in a container, because if you put that in a public repo, everyone has access to it. It's not what we want to do. So configuration, and particularly if you have data in a database, should never be in there because it's an immutable container. They come from the outside, and we inject them with that -v command once we run the container. And hence, I can run the same container in different environments with different settings without changing anything. And that's pretty darn powerful, but just remember that when you build the container that they don't belong in there. So the last demo is going to be about building a container. So I made a extremely small Dockerfile. Actually, it doesn't really matter. I'll take this one. So there's my build command. I'm going to write a container on what's called the universal base image from Red Hat. This is a free version of RHEL. Anyone can pull them down. You do not have to register anywhere to get it. And it brings down a very, very basic version of RHEL. And then I'm going to add on top of that a very simple little cat that allows me to write to the web network port. And basically all I'm going to do is to type that out when people are coming in. That's basically it. So to run that, now, sorry, I cheated a bit because I've already downloaded the image. So I did this again yesterday. I want to be sure it worked. But it basically ran those commands that you just saw up here. And as you notice, after each time, it created a new image. Notice that? And now when I do a podman images, I should see it. So it actually created it in here. Let me actually add a tag to this so we can make sure we all see the same thing. Tag my demo 3, podman images, and I should see my demo 3 right there. Look at that, it's right there. So now if I say podman run, and notice that, oops, I'm gonna do this cheat again. So in the build, no, it should have said that on the screen. No, see here. And that may have been my mistake, is that I did not do the port switch, the entry point. So let me actually make sure that that works, but yeah, see, connection refused. So let me go ahead and put that entry point in there. See, that's what happens when we do demos. Okay. You should still have all 3. I've got a new ID because I made the change. And what I'm going to make sure is that I'm actually exposing 06, and I'm going to go over here again and try again. Oh, true. Not an HTTP port. But as you can see, I talked to it. It didn't, forgot how to do the demo thing here, sorry, but NC probably works. Which is not on this box, sorry. I hope this is enough to see I actually talked to it, but because this is not a web thing, it's just a raw port. It's supposed to come back with this little hello, I'm a database thing. And right now, because I don't have NCAT on this box, I did not demo it because I've done it on so many other boxes that but yet I don't have NCAT on it. But anyway, you can see I'm actually accessing it, and because it's not a web server, it's going to block me. I actually had another image on here with a web server on it. This guy here. Oh, I showed you that already. I showed that earlier. And you saw me accessing that. But anyway, you saw it actually, it is responding, it is running. And all I had to give it was this Dockerfile here. And that expose is required for me on the host to be able to see what's coming out. So a container could say, hey, I'm exposing 5 different ports. But as the admin, I may choose to only expose one of them, meaning to give that onto my host. And no one else can see those ports. The only one that can see the internal ports is the container itself. Now, once we get into Kubernetes, it gets a little more fun because now everyone inside the same pod can see those ports. But yeah, that doesn't really matter today. We will talk about that next month. But that's going to pretty much do it. Sorry about this last demo not really working the way I planned it to do. But I try to keep this as short as possible. There is a ton of material. If you go to that link that is on top of my screen there again, the learn.openshift.com link, and go to some of the 7 different labs they have, they get more and more advanced as you go on. It links to a presentation, and that presentation has a lot of the slides that you show here and a lot more. Yes.
Are you sure it's subsystem and not subsystems? Because both resolve to a website, and I think you want subsystems. think if you add the S, it'll give you what you were aiming for.
Could be. Yep, you're right. Good catch. Thank you.
That was caught earlier on in the chat.
Very good. Thank you very much.
So my question is it Potman? Potman?
Yes.
POD
Oh,
is in Docker.
oh, DMAN, because I didn't see it in my repository here. Doing what it.
So the word podman comes from, again, a lot of the container stuff in these world in the current world is happening in the Kubernetes world. And in Kubernetes, we don't run containers, we run pods. And a pod is one or more containers. So podman was named based on that whole fact. And podman is compatible and understands the Kubernetes terminology here. So it can create pods and manage pods as well as containers. That's why it's called pod. We will get into why that makes a difference and why that is cool later in next month, but that's why it's called podman. And one thing I have not demoed today, and I do not have the time, is we often need to be able to start a container automatically on boot. Now, this is where, because Docker is a daemon, that Docker sort of does that in a little bit different way than Podman can. So because the daemon is, when you install it in Docker, you set that daemon to start and boot. Then that daemon can then easily figure out what do I need to do when I'm booting. And so there's a flag in Docker where you can say, start this container on boot. It's actually called restart it regardless of what happens, and that is a reboot. And we don't necessarily do that. Well, we can't do that with Podman because there is no daemon. Right? There is no. Well, that's because I didn't exit it right. There shouldn't be a. It's still there. I'll have to be a little more insistent on killing that, but it shouldn't matter. Doesn't matter. Because there's no daemon to stop and start container, as you can see, I have two running here. So if I want to do a auto starter, I use systemd. There we go. This is by far the simplest way of setting it up. So what this does is create the whole unit. And all I have to do, I can basically do, if I had the root rights, I can do a use of something, right? And plug it into here, my container. But I don't have write access, so I can't plug it in there. But that's all I need to do to define it. As you can see, it is a little more complex than a single start line, which is why that generate systemd is so much easier. Once you have done that, now every time you change the container, it gets a new ID. So you have to update that or go in, and that's what I typically do. I replace this with the name of the container instead. That way, when there's an update, it still gets a hold of the right version of it. But that's really up to how you want to do that on your own. But that's about it.
Wow.
Thank you, Peter.
Thanks a lot.
I hope this was helpful. As I said, this has been my day-to-day life, most on, not off, for at least 5 years, if not longer, depending on how you look at it. But I see this as the new face of Linux, basically. This is how things work in the future. We've all seen Flatpaks. We've all seen these new ideas of distributing software, even for end users like GUI commands and all that, all coming packaged in the same way containers are. And it's a big advantage to me that someone can now create a great project. They can come up with the best idea ever, and they can package it in a way that works in most distributions out of the box without any modifications. That's a win-win to me. Dark sides to that, but we can get into that next month, maybe if there's interest, or why we have to also be cautious about it.
Well,
yeah.
but my thought, though, is that since you don't have any configuration in the containers, then you have to the run command of it is a lot more complicated. You have to mount all the things and make sure you have a lot of pieces here.
So you're right. If you're running a container raw, like we're doing right now, there's a lot of things you have to remember to put in. I will not reject that. That's what the container runtime platforms do. That's what Kubernetes changes.
I see.
In Kubernetes, it's a one-time definition to say, here's where all my configuration stuff is, here's where my container is, go run it. And once it's done, when I change let's say there's an update to my container, my configuration stays put, and I don't have to tell it again how to do it. So it's done for me, and I only have to define it once. But you are absolutely right that when you run stuff, you have to configure it. But that's no different than today. Like, if I want to run Apache or Nginx, it's not enough for me to just say yum install. I got to go in and define several configuration files to make it work. And that still is the case with containers. Now, some of it is a lot easier. Once you get into a container platform, I don't have to find SSL and doing all the endpoint security that I used to have to do on a VM. All of that is taken care of by the platform. But again, I'll get into how that helps. But I still need to configure if I want to run PHP, if I want to run Python, or if I want to run something else in there that has to be configured and set up the right way. And if you don't do it the right way, it won't work, it won't run. We have, there's 4 people. So about half of people who signed up. Cool. Well, with that said, then I will stop half an hour early. Now, unfortunately, when I close this, it's going to close the meeting out. First, I'm going to stop the recording.
Which